Swayam Prabha. Digital India. Educated India.
Welcome to today's lecture for NPTEL video course on Geotechnical Earthquake Engineering. So, for this video course, currently we are going through the module number 9, which is the last module of this video course, which is on seismic analysis and design of various geotechnical structures. Before I go to the recap what we have studied in the previous lecture, just I want to share a latest news on major earthquake which has occurred in Iran on 16th of April 2013, just few days back of before we are recording this video. You can see the event time, the details are given over here, location, latitude and longitude is given over here. The magnitude was 7.8 earthquake. So, it was very devastating earthquake in Iran, which was felt far away even in New Delhi of India also. So, it occurred on Tuesday, April 16, 2013. All these details are collected from this USGS website, that is http earthquake.usgs.gov, which gives us authentic information as we have already mentioned and discussed during this course. These are some of the tectonic summary which is provided by USGS about this magnitude 7.8 Iran earthquake which occurred on April 16th of 2013. You can see over here it is because of the collision between Arabian plate and Indian plate with Eurasian plate. So, these three major plates are moving, and because of that movement this collision occurred, which caused this earthquake of 7.8 magnitude to occur on this day. And though this subducted Arabian plate is seismically active, but not as much active as other subducted plates worldwide, but still you can see over the last 40 years there are few large magnitude earthquake like 6.7 magnitude earthquake in 1983, then in 2011 January 7.2 earthquake, and the present one, that is April 16, 2013 7.8 earthquake occurred because of this subducted Arabian plate movement. This shows the USGS shake map at Iran-Pakistan border for this 16th April 2013 magnitude 7.8 earthquake, which is provided by US Geological Survey USGS website. You can see from this shake map that the intensity, the modified Mercalli intensity scale or MMI scale is about this 8. This is the magnitude. So, there was about the population of 2000 people were exposed to this severe intensity of earthquake 8 intensity, and about 3,77,000 people were subjected to MMI scale of about 7, as has been detailed in the USGS website. So, this way, as we have already discussed, whenever there is a large earthquake worldwide, we also experience the information through the collection of the data during and after the earthquake. So, these earthquake data obviously will benefit the earthquake researcher in the form of to better estimation or probabilistic hazard estimation and ground response and various other geotechnical earthquake engineering related aspects for collected from these earthquake data. Now, let us do a quick recap what we have learned in our previous lecture. This is combined pile raft foundation CPRF under earthquake conditions we were discussing. For that, we have already learnt what is combined pile raft foundation. There are several examples are existing in practice, like Messerturm Tower in Frankfurt am Main in Germany. Why we go for combined pile raft foundation instead of only raft or only pile, that also has been discussed earlier, and the extensive research work carried out by Professor Katzenberg of Technical University Darmstadt in Germany has been mentioned over there. The basic concept of pile raft combined this foundation, combined pile raft or CPRF foundation, is through the pile soil raft interaction process. So, this is a complex interaction where these major 4 types of soil structure interactions are involved, and the total load carried by the entire foundation shared by pile as well as the raft. So, this is the analytical study which gives the details about sharing of load between pile and raft, and from that we also mentioned that CPRF coefficient is the design parameter which needs to be at 50% or 0.5. That shows the best design, because then pile and raft shares the equal amount of load coming from the superstructure. So, alpha CPRF or CPRF coefficient is generally set between 0.45 to 0.55 for design purpose. Then we discussed about the research work carried out by Eslami et al. In 2011 using abacus. The analysis was carried out for combined pile raft foundation under dynamic loading condition. So, the dynamic loading response, as can be seen from this picture, input acceleration of 1 meter per second square with input frequency of 1 hertz was applied, and it was observed that compared to the pile group acceleration response, in the combined pile raft there is a 36% decrease in the acceleration value. So, which is beneficial of course. As well as you can see from this results of Eslami et al. 2011, it shows 54% decrease in the pile raft model in the amount of bending moment along the pile length. Also, they carried out the research for the seismic loading conditions using L centro acceleration time history, and it was found that there is 34% reduction in acceleration value compared to pile group in case of combined pile raft foundation. And for horizontal displacement response under this El Centro earthquake, they observed that there is a 9% reduction in the displacement for the pile raft compared to the pile group values. So, that automatically showed, and we have discussed in our previous lecture, the importance of combined pile raft foundation even during the earthquake condition. Then we also discussed about a case study of how a combined pile raft foundation behave during an earthquake. So, for that case study, the Tohoku earthquake of 2011 March in Japan, that earthquake response was considered on a constructed pile raft foundation with these details given over here, and it has been reported by Yamashita et al. In 2011. We have already learned from this that this place was 270 kilometer away from the epicenter where this foundation was constructed, combined pile raft foundation, with the soil characteristics, SPT value and shear wave velocity value reported over here. Then it was observed that there were instrumented piles, pile P1, P2 and P3. Instrumented pile P1 observed the ratio of load carried by the pile. This is the effective load and this is the total load. So, after March 11, 2011, that is the date when the big Tohoku earthquake occurred, after that there is very marginal decrease. So, there was not much of a decrease over here, whereas for pile 2 there was little more significant decrease, but not that much, which can show that combined pile raft foundation is not performing good. In the other word, it is performing better combined compared to the only pile foundation. So, you can see here the values of decrease of this load ratio taken by the pile after the earthquake. Then in our previous lecture, we also talked about this seismic design of ground anchors, and I have mentioned this is a part of PhD thesis work done by Dr. Sunil Rangari at IIT Bombay under my supervision along with my colleague Professor Divakar. So, we have already learned what are the use of ground anchors, we know about it, and whenever there is an earthquake or it is designed in seismically active region, obviously we need to take special care for the design of this ground anchors, which will be subjected to uplift or pull out load. Then basic simple model which was given by Dr. Rangari in his thesis, that under earthquake condition for a horizontal strip anchor subjected to vertical load, these are the inertia forces. These were computed both using pseudostatic as well as pseudodynamic approach, and Coter's equation of 1903 was used for finding out the soil reaction on these assumed planar failure rupture surfaces. Finally, the typical design values of this uplift capacity factor under seismic condition F gamma d has been proposed with variation of kh and kv, that is seismic acceleration in horizontal and vertical direction, for various values of soil friction angle phi and for selected particular values of embedment ratio of anchor plate. And using both pseudostatic approach as well as pseudodynamic approach, the design charts or results have been given. The details can be obtained in this journal paper of 2013 by in the journal Geotechnical and Geological Engineering, Springer publication. This is the volume and page numbers. Then the results have been compared, the results of Rangari et al. Along with the other researchers' results, and it can be obtained that the present study give in most of the cases the critical design values of this seismic uplift capacity factor, ultimate seismic uplift capacity factor, which is necessary for the design of this ground anchors in seismically active region. Also for the inclined strip anchors under seismic condition, the analysis was carried out by Dr. Rangari, and the details of this analysis is available in the journal paper in journal Disaster Advances. This is the volume number and page number. This is the basic model which was considered using Coter's equation for planar failure surface. And we had already learned that closed form solution for net seismic uplift capacity factor F gamma d was proposed like this, and from which we can obtain the QUD net, which is nothing but net ultimate uplift capacity for the anchor for a particular value of embedment ratio as well as the seismic passive earth pressure coefficient. Then critical failure angles also were obtained by optimizing the different failures angle alpha 1 and alpha 3 for different cases of earthquake accelerations. Finally, the design charts are also proposed for this obliquely loaded as well as inclined strip anchors like this, and results have been compared with only available one inclined anchor results theoretically in the available in the literature like this, and it shows the present results gives a very good estimation with the available result. So, we will start now today's lecture with the topic, another subtopic or new subtopic, seismic behavior of municipal solid waste landfill. Municipal solid waste, we will abbreviate it as MSW landfill. This work is carried out by Dr. Purnanand Savaikar. He completed his PhD in 2009. It is his PhD thesis work, which was carried out at IIT Bombay, Mumbai, India, under my supervision, along with my colleague Professor Mandal, who was co-supervisor for this PhD thesis work. As we all know from the basics of municipal solid waste landfill, what are the various components of municipal solid waste landfill? This is a typical picture which shows various parts of the municipal solid waste landfill, which are used for engineered landfill design, and this is taken from the Kavazanzian et al. 1998, who did extensive research work on this seismic municipal solid waste landfill design and its behavior. The first step to understand the properties of this municipal solid waste landfill under earthquake condition or under dynamic condition is very necessary for further design of this municipal solid waste landfill. Why it is necessary? Because unlike soil, municipal solid waste material are completely different type of material. Also, in most of the cases, they will be in the loose state, not in compacted or consolidated state. So, it is necessary for us first to understand the dynamic properties of municipal solid waste material. So, in the work of Dr. Savaikar's PhD thesis, he used extensive literature which are available in various journals and conference papers, and collected all those literature, whether it is theoretical or analytical or experimental or field study results. Those values he has taken, and finally, from the collected worldwide data of municipal solid waste material properties, he estimated the unit weight of waste material, which is varying with respect to depth. As you can see, there is a wide range of variation of gamma of waste, unit weight of waste material, which is expressed in kilonewton per meter cube with depth in meter. There is a wide range of variation as collected all over the world, but using all of them and taking from this local coordinate system to a global coordinate system, mentioning the parameters in such a way that all the data points comes in a narrow band, which is of course not visible in this direct axis system, but if somebody wants to plot in this form, as you can see over here the equation, it gives a very good estimate with the regression coefficient R square value of 0.99, and this equation can be used when somebody wants to do a preliminary design of municipal solid waste material, when they do not have the value of gamma of waste available varying with respect to depth for this seismic design of municipal solid waste landfill. So, in absence of actual field data, one can easily use this proposed equation, which was proposed by Chaudhary and Savaikar. This is available in this journal paper of 2009 in the journal paper Waste Management. Waste Management is a Elsevier journal. This is the volume number and page number. Further, the shear wave velocity, another important parameter. Now, another very important dynamic property of municipal solid waste material, that is shear wave velocity, Vs value in the unit meter per second, how it varies with respect to depth of municipal solid waste landfill. All these data points are collected from the available literature worldwide. As you can see over here, various researchers work, extensive research work done by Professor John Bray and Professor Radje. All these research papers of 1998, Kavazanzian et al. 1994-1995. Then Earth Technology, Woodward Consultant, Carey et al. And so many other researchers work, including the Zako's work. So, from the collected data, once again the analysis was carried out to propose a semi empirical correlations of this worldwide data, which will give a good value of regression coefficient by taking these two parameters into different scale level, and the proposed equation is given over here. So, in absence of the exact shear wave velocity data for the design, in the preliminary state, people can use our proposed design over here at any particular depth, what will be the typical value of shear wave velocity for a municipal solid waste material, as it is reported in this journal paper also. Next important dynamic property of municipal solid waste material is nothing but material damping. So, material damping, this axis is in percent and this x axis is cyclic shear strain in percent. You can see over here, all these are again collected data points worldwide, through which the semi empirical relationship has been proposed over here. So, depending on the earthquake shear strain value, one can estimate what will be the material damping. This damping curve is very necessary, as we know, for doing any ground response analysis or site response analysis. So, if we want to carry out the ground response and site response analysis for municipal solid waste landfill, in that case this material damping curve needs to be used, not the conventional soil damping curve. Further, the normalized shear modulus, that is G by G max ratio, this curve, how it varies with respect to cyclic shear strain, that is nothing but modulus reduction curve, how it varies. Those data also have been collected from the worldwide researchers' data points, which are proposed in various research papers, in journals and conferences, technical reports and PhD thesis, like Zeko's PhD thesis at UC Berkeley, then Kavazanzian, Matazovic, Seed and Idris, Kavazanzian et al., Idris et al., and so many other researchers, Singh and Murphy. From this collected results, again a semi-empirical correlations were proposed, which gives R square value of 0.996, a very high value. By having this equation, one can easily do a preliminary design or can carry out site response analysis for this municipal solid waste landfill material using this value of cyclic shear strain, what will be the corresponding value of G by G max, which is helpful for any seismic design of municipal solid waste landfill. Now, once this dynamic characterization of this municipal solid waste landfill is over, then we can start to carry out either equivalent linear or nonlinear analysis for this municipal solid waste landfill. As we have done for the soil, various soil site, it is site specific, as we have mentioned. Here also it will be the material specific. So, in this case the municipal solid waste material dynamic property needs to be incorporated for doing the site response analysis. So, this slide shows how the seismic ground response analysis for this municipal solid waste landfill were conducted. Typical landfill like this was considered, and this is the base of the landfill, height of the landfill, and the foundation material, different types of foundation material were considered. This is on the rock type foundation, this is on foundation soil, various layers of soil with different values of gamma and Vs, followed by a rock. Then another MSW landfill, which is founded on another type of soil, that is 2 soft clay followed by sand and then rock, and another landfill which is constructed on foundation soil like stiff clay followed by a soft clay, sand and rock. So, various layers and various combinations of foundation soil was considered for this seismic ground response analysis, which has been carried out using this software Deep Soil, and also later on it has been carried out using the software FLAC 3D. And for the analysis, there are various types of earthquake motion like Kobe earthquake motion, Loma Prieta at another recording station. So, these input acceleration time history were used to carry out this seismic ground response analysis for municipal solid waste landfill. That is, the soil properties as well as landfill properties needs to be considered. The details about this work is available in this journal paper, Chaudhary and Savaikar 2009, in the journal Engineering Geology, which is an Elsevier journal. This is the volume number and these are the page numbers. You can see here that this slide shows the typical results as obtained by Chaudhary and Savaikar in this paper, as I have mentioned just now. This shows how the maximum horizontal acceleration, or MHA, in the unit of g, it varies with respect to the elevation. Elevation, you can see over here, the 0 line shows the landfill base and below that is the foundation soil. So, for different foundation material, it has been considered different results, and on top of it, it shows the behavior within the landfill. So, from this figure one can easily see this is the for the foundation type 2, only for a specific foundation type, and landfill height was considered 40 meter. 40 meter is the height of the landfill, and base acceleration, these are 4 different types of seismic acceleration was considered as input motion. You can see over here there is huge amount of amplification, that is increase in this value of this maximum horizontal acceleration when you are considering at the base of landfill and at the top of landfill in all these 4 cases of input acceleration. It automatically shows that the landfill material which are in the loose state, they amplify much more the input motion, which has been validated and proved through this observation and results. Similarly, the spectral amplification is shown over here for various input accelerations for this landfill of height 40 meter, which is founded on type 2 foundation. Type 2 is nothing but as shown over here, this is type 2 foundation, and variation along with frequency, it has been shown over here. So, these are very useful when somebody is going to design any landfill of say 40 meter height at this site using this type of foundation soil. And as we have already mentioned, to characterize the municipal solid waste material in terms of its dynamic property like Vs value, G by G max value and a damping ratio value, including the unit weight, they can use our proposed equations and finally can obtain what will be the amplification etc., which further will help to design this seismic, this municipal solid waste landfill in the seismically active region, so that there is no failure, because we know whenever there is a failure of this municipal solid waste landfill, it will not only create a disaster in terms of damage of the landfill itself, but it will also initiate the process of leachate leaking and various others environmental hazards, which are additional damages to the society and locality. Another results have been shown over here. You can see in this case landfill height is 20 meter for a single base acceleration of 0.834 g was shown over here, how the maximum horizontal acceleration is changing for different types of foundation, for different 5 types of foundation, depending on foundation soil also the behavior of this seismic amplification of this maximum horizontal acceleration within the landfill will depend on, as can be also seen from this results. As well as you can see from this, if somebody considers the variable stiffness, this solid line shows the behavior of maximum horizontal acceleration within landfill and in the foundation soil, instead of considering constant stiffness. Why it comes into picture? If we go back few minutes back, what we have discussed when we have characterized the dynamic properties of the municipal solid waste landfill material with depth. So, in the variation with depth, there is a change in the value of G by G max and Vs values etc., that will automatically change depth wise the stiffness. If somebody wants to consider that variable stiffness which varies with respect to depth, that will give more correct result rather than assuming a constant stiffness throughout the layer. So, that is what it has been carried out and shown that in terms of constant stiffness within landfill region, that is from base of landfill to top of landfill, here the amplification of MHA value was this much, whereas in this case amplification was this much. So, obviously, amplification is much more if somebody considers the variable stiffness, and moreover it gives a more realistic results as shown over here. Now, this slide shows the comparison between the results obtained by using 2 different softwares. As I have mentioned, one is deep soil, another is FLAC 3D. One can see here easily these solid lines shows the results obtained from deep soil analysis, and the dotted line shows the results obtained from the FLAC 3D analysis. As can be seen in most of the cases from this present study, what we had considered with the given input values and this given input seismic accelerations, in most of the cases the deep soil gives a higher results for these type of landfill, except this landfill where for Kobe earthquake motion one can find out that FLAC 3D results are showing much higher than the deep soil results. It depends on various characteristics of soil, various characteristics of seismic input motion and so on. Also, the normalized shear stress, how it varies with respect to depth as obtained in deep soil and FLAG 3D are shown over here. The details about this work can be obtained in the publication Savaikar and Chaudhary 2010 in the proceedings of 6th International Conference of Environmental Geotechnics in New Delhi, volume number 2, and these are the page numbers. Now, once this dynamic characterization of municipal solid waste material is complete and ground response analysis is complete, next step is how to design a safe, stable municipal solid waste landfill in the seismically active region. So, for that the seismic stability analysis of municipal solid waste landfill has been carried out, as can be seen from this basic picture. There are various types of landfill, as we know. Here in this picture only hill type municipal solid waste landfill has been shown, which is founded on a sloping base. So, this is the sloping base. So, this is hill type MSW landfill. There are various other like cannon type, side hill type, various other types of landfill, and in different regions, by considering the seismic inertia forces using the pseudostatic as well as later on using pseudodynamic approach. This work, as I have mentioned, was carried out Dr. Purnanand Savaikar during his PhD at IIT Bombay under my supervision. This is the equation of factor of safety for this stability of this slope were arrived at after considering equilibrium of all the forces involved. So, this is the typical results of factor of safety one can see, which is varying with respect to L by H ratio for different input values of Kh and Kv combinations with these given parameters. As it is seen, at some of the cases the factor of safety may go below 1. That means, we need to find out the yield acceleration for those cases and also want to estimate the displacement. So, the expression for yield acceleration is given by this, where various parameters like x is given by this ratio of Kv by Kh, and this tan of psi is expressed as this, which can be estimated from these values given in this equation. And these are the results which shows a comparison of pseudodynamic and pseudostatic method. The solid line shows the pseudodynamic results and dotted line shows the pseudostatic results of factor of safety varies with respect to the seismic horizontal acceleration. And you can see here pseudodynamic method is giving in most of the cases for this chosen set of input data little higher value than the pseudostatic results. And the yield acceleration coefficient value, the Ky, which is varying with respect to L by H, you can see over here the pseudodynamic gives a more critical value than the pseudostatic results. Further, the analysis was carried out for seismic stability of MSW landfill. This is for side hill type landfill, another type of landfill which is called side hill type. So, this is the slope of the hill and this portion is the landfill. So, by considering two zones, that is active wedge zone and passive wedge zone, involving all the forces which are present in this zone, then limit equilibrium of all these forces are considered to carry out the stability analysis, and finally, the factor of safety, average factor of safety has been reported, considering also the cohesion component of municipal solid waste material as well as the cohesion of the soil. So, these are the variations of pseudodynamic and pseudostatic results of factor of safety, whereas this picture shows the effect of field amplification factor, which is not possible to consider in pseudostatic method, but we can consider only in pseudodynamic method, as we have discussed earlier also. And you can see as the field amplification increases, there is a significant decrease in the value of this factor of safety of this MSW landfill slopes. So, as we have already learned from the ground response analysis, equivalent linear ground response analysis for MSW landfill, that there are always some amount of amplification, seismic amplification. So, one needs to consider this amount of amplification when somebody is designing the MSW landfill for the stability of the slope in terms of translational failure or rotational failure like this, and then factor of safety and yield acceleration needs to be estimated. Some more results of factor of safety for both pseudodynamic and pseudostatic results with respect to B by H ratio are shown over here. The details about these results are available in the journal paper by Savaikar and Chaudhary of 2010, available in the journal Waste Management and Research. This is the volume number and page number. Now, another important aspect of this MSW landfill, because of scarcity of available space or land in urban areas, like in Mumbai, somebody will find it very difficult to find an open land to construct a new structure or building or a very big structural things in Mumbai to find out an open space. Because of this problem of space crunch in urban cities, not only in Mumbai, but in other urban cities worldwide, like in Tokyo, in New York, in Frankfurt and all these places, there is a need that whenever this engineered landfill, that is the landfill which are designed using the engineering methodology, and after closing of this landfill, if somebody wants to use that space for further construction, and if a seismic event is supposed to happen at that place, then what are the extra precautions needs to be considered for the design of this landfill, and if there is a need for extension of the landfill, because many a cases, because of the space crunch, horizontally the landfill may not be able to get expanded, one need to go for vertical expansion of landfill or a combination of vertical and horizontal expansion of landfill, and further the use of that landfill area for further civil construction. So, in this slide we are now going to discuss about the seismic stability aspects of the expanded MSW landfill. That is, this is the original berm, and on that a new landfill or expansion of landfill has been proposed over here over the existing landfill like this, and a berm has been provided over here to maintain the stability. This is existing landfill, this is new landfill. It is not in scale, but it gives a schematic diagram of how the expansion of landfill can be carried out, and the seismic stability aspect of this expanded landfill also needs to be ensured. The details about this research work is available in the journal paper by Chaudhary and Savaikar 2011 in Waste Management and Research. This is the volume number 29 and page numbers. So, all the forces are given over here. There can be two possibility mode of failure for this new landfill over the existing one. One is known as bottom berm failure, another is upper berm failure. So, considering this berm failure, one can easily find out using the limit equilibrium approach for all the forces involved in the basic picture what I have shown just now. What is the factor of safety of that expanded landfill region depending on various other input values like back slope of the berm, and using either pseudodynamic approach or pseudostatic approach. In these results, one can see the pseudodynamic approach gives a least value or critical value compared to pseudostatic approach. Also, for the average yield acceleration coefficient, the pseudodynamic approach gives the least value or the critical design value compared to the pseudostatic approach. So, with this we have completed our module number 9 for this video course, and that was the last module for this course. Now, before I wind up the entire video course, I would like to acknowledge various people who helped me while making this presentation and also to understand the subject, and also through my collaboration and research work carried out with my students, with my collaborators, with my teachers and various other funding agencies. So, these are the acknowledgement goes like this. First of all, I must thank my former PhD scholars, total 10 PhD scholars who have completed PhD at IIT Bombay under my supervision, either as myself as main supervisor or co-supervisor. Among those 10 PhD scholars who have completed already at IIT Bombay their PhD thesis, 7 of them did work under my direct supervision as myself as main supervisor. Their names are Dr. Sanjay S. Nimbalkar, Dr. Syed Muhammad Ahmed, Dr. Purnanand P. Savaikar, Dr. V. S. Fanikant, Dr. Sumed Y. Maske, Dr. Jaikumar C. Shukla and Dr. Sunil M. Rangari. Also, I want to acknowledge the research work carried out by my ongoing PhD scholars or current PhD scholars who are working under my supervision at IIT Bombay, like Mr. Amay D. Katdare, Mr. Ranjan Kumar, Ms. Sarika Desai, Ms. Nisha Nayak, Ms. P. Shailamani, Mr. Kaustav Chatterjee and Ms. Reshma Raskar Phule. Now, while acknowledging my PhD students who are the main pillars for the research work in this area of geotechnical earthquake engineering, I want to share this information with all of you that what are the doctoral thesis or PhD thesis which are completed at our lab, that is at Geotechnical Earthquake Engineering Laboratory at IIT Bombay at my laboratory. As I have already mentioned their name, this slide shows their thesis title and at present where they are working, all these details. Like Dr. Sanjay S. Nimbalkar, he completed his PhD in 2007. His topic of research was seismic analysis of retaining walls by pseudodynamic method. As I had already mentioned and discussed several times, he developed pseudodynamic method extensively. Currently, he is a research fellow at University of Wollongong in Australia, and this research work was supervised jointly with Professor J. N. Mandal of IIT Bombay. Next, my second PhD student, Dr. Syed Muhammad Ahmed, who completed his PhD in 2009. His PhD thesis topic was seismic analysis and design of waterfront retaining structures using pseudostatic and pseudodynamic approaches. As I have mentioned, he first worked on this combined effect of tsunami and earthquake using this pseudodynamic approach as well as pseudostatic approach. Currently, he is a lecturer at University of Manchester in UK, and this thesis was supervised by myself alone. My third PhD student, Dr. Purnanand Savaikar, who also completed his PhD in 2009, his PhD thesis topic was seismic behavior of municipal solid waste landfills, as I have discussed just now about his work. Currently, he is head of civil engineering department at Government Polytechnic in Goa, and this PhD thesis was jointly supervised with Professor J. N. Mandal, who was co-supervisor for Dr. Savaikar. Next, Dr. Vivek B. Deshmukh, he completed his PhD thesis in 2010. His PhD thesis topic was some studies on uplift capacity of pile anchors and horizontal plate anchors. Currently, he is an associate professor at Department of Structural Engineering at VJTI in Mumbai, and this thesis was supervised jointly with Professor D. M. Dibaikar of IIT Bombay, who was the main supervisor for this student. Next, my PhD student, Dr. Vedula S. Fanikant, who completed his PhD in 2011. His PhD thesis work was on ground response analysis and behavior of single pile in liquefied soils during earthquake. As I had already discussed about his work, he developed the new method how to incorporate the local soil conditions like Mumbai soil condition to carry out the ground response analysis, and further to incorporate that effect in the pile analysis in the liquefiable and non-liquefiable soils during earthquake. Currently, he is a scientist G at Bhabha Atomic Research Center in Mumbai, and this thesis was supervised jointly with Dr. G. R. Reddy of BARC, who was the external co-supervisor for Dr. Fanikant. Then Dr. Raghunandan M.E., who completed PhD in 2011. His PhD thesis topic was effect on cyclic response and liquefaction resistance due to desaturation of sand. Currently, he is an assistant professor at Monash University, Malaysia campus, and this thesis was jointly supervised with my colleague Dr. A. Juneja, who was the main supervisor for this student. Next, my student Dr. Sumed Y. Maske, who completed his PhD in 2011 at IIT Bombay. His PhD thesis topic was GIS GPS based geotechnical studies for seismic liquefaction hazards in Mumbai city. I have described about his work, how to prepare the liquefaction hazard map and what is the use of that hazard map in the mitigation of the disaster after the event of earthquake has occurred at a particular city, how to find out the rescue operations, etc., and the dynamic soil properties and other things, how to map it in the GIS GPS based interface, which is useful for the designers in a particular city like Mumbai. So, currently he is head and associate professor in Department of Civil Engineering of VJTI in Mumbai, and this thesis was supervised by myself alone. Next, Dr. Ganesh S. Kame, who completed his PhD in 2012. His PhD thesis topic was analysis of a continuous vertical plate anchor embedded in cohesionless soil. Currently, he is professor at Department of Civil Engineering in this college in Mumbai. This thesis was supervised jointly with my colleague Professor D. M. Dibaikar, who was the main supervisor for this candidate. Next, my PhD student Dr. Jayakumar Chandrakant Shukla, who completed his PhD in 2013, very beginning. His PhD thesis topic was seismic hazard estimation and ground response analysis for Gujarat region. I have already discussed in detail about his research work, how to carry out the seismic hazard analysis using both deterministic seismic hazard as well as probabilistic seismic hazard and ground response analysis, and further to apply those in various cities and ports of Gujarat. So, currently he is an engineer at L&T Sargent and Lundy in Surat. This thesis was supervised jointly with Professor D. L. Shah of MS University, who was the external co-supervisor. Next, my PhD student Dr. Sunil M. Rangari, who also completed his PhD in 2013. His PhD thesis topic was seismic uplift capacities of horizontal and inclined strip anchors in cohesionless soil. Currently, he is assistant professor in a college in Mumbai. This thesis was also supervised jointly with my colleague Professor D. M. Divaikar, who was the co-supervisor for this candidate. So, you can see there are many students who worked in this laboratory of geotechnical earthquake engineering at IIT Bombay, and from their work my course of this geotechnical earthquake engineering has been majorly developed, and the work research work mainly in various modules what I have mentioned are given over here. So, currently 7 more PhD students are working in various topics related to this geotechnical earthquake engineering at IIT Bombay under my supervision, as I have already mentioned their name. Next acknowledgement goes to all my master students who worked under my supervision at IIT Bombay for their master's dissertation and master's thesis. First, I want to acknowledge the work carried out by my former or previous master student, namely Mr. Shantiram Chatterjee, Ms. Somdatta Basu, Mr. Rajiv Kumar Bharti, Ms. Deepa Modi, Mr. Mayuk Mukhopadhyay, Mr. Manoranjan Tripathi, Mr. Debarghe Chakravarti, Ms. Gayatri Dandekar, Ms. K. Sangeeta, Ms. Ritika Sangroya. They have done excellent master's dissertation work, and some of their work I have also mentioned in this course while discussing about various research aspects, design aspects and findings. Also, my current MTech students who are also currently doing their MTech dissertation work at IIT Bombay under my supervision, like Mr. V. Dilli Rao, Mr. A. Sarin, Mr. R. P. Singh and Mr. Ashutosh Kumar. Next, my thanks goes to my supervisor, my teachers in India, like my PhD supervisor Professor K. Subbarao, with whom I did my PhD at IISc Bangalore in this area of geotechnical earthquake engineering, and also my another teacher Professor A. Sridharan, who also worked extensively in the area of soil dynamics and machine foundations. I worked with him at IISc Bangalore as well. Then Professor T. G. Sitaram, Professor G. L. S. Babu, Professor J. Kumar, Professor C. S. Monohar of IISc Bangalore, from whom I have learned various aspects of soil dynamics or geotechnical earthquake engineering or structural dynamics. Also, I want to acknowledge the help of Professor N. N. Som, Professor R. D. Purkayastha, Professor S. C. Das, Professor P. Bhattacharya, Professor S. P. Mukherjee and other teachers of Jadavpur University, who taught me various aspects of foundation engineering, though those things are not directly related to this geotechnical earthquake engineering, but the concept of geotechnical engineering, their application in foundation design etc. were developed and given by these teachers of mine. My various collaborators in India with whom I have worked, and with some of them I have also joint publications which I have discussed during this course, and some of them are also currently working with me, and I am happy to acknowledge their help in this slide, like Professor M. R. Madhav of JNTU Hyderabad, who was former professor at IIT Kanpur. Then my colleague of Professor J. N. Mandal, Professor D. M. Divakar, Professor B. V. S. Vishwanatham and Professor S. Ghosh of IIT Bombay, Professor Priyanka Ghosh of IIT Kanpur, Dr. G. R. Reddy, Dr. K. Bhargava, Dr. A. K. Ghosh of BARC Mumbai, Dr. P. C. Basu of AERB Mumbai, Professor D. L. Shah of MS University Baroda, Professor P. Samui of VIT, Professor G. Bhattacharya of BESU, Professor A. M. Krishna of IIT Guwahati, Professor C. Ghosh of NDMA. Now, my other collaborators from outside India with whom I have worked at various times, and also currently with some of them I am working. Also with some of them I got various publications either in this area of geotechnical earthquake engineering or the related area. So, I want to acknowledge their help, like Professor Jonathan D. Bray of UC Berkeley, USA, Professor Buddhima Indraratna of University of Wollongong, Australia, Professor C. F. Leong of National University of Singapore, Professor Ryosuke Kitamura of Kagoshima University, Japan, Professor Rolf Katzenberg of Technical University Darmstadt, Germany, and Professor S. Bhattacharya of University of Surrey in UK. I must acknowledge the funding agencies, the major or significant funding agencies like AERB Mumbai, BRNS DAE Mumbai, INAE Indian National Academy of Engineering New Delhi, ACRC DST Department of Science and Technology New Delhi, INSA, that is Indian National Science Academy New Delhi, IRCC of IIT Bombay Mumbai, India. So, these are the national funding agencies, and also various international funding agencies like Alexander von Humboldt Foundation of Bonn, Germany, Japan Society for Promotion of Science, Tokyo, Japan, UKIERI of UK, India jointly, Samsung C&T of Korea. And a special thank goes to Mr. Kaustav Chatterjee and Mr. V. Dilli Rao, who are my current PhD student and my MTech student, who helped me to prepare the various slides and to edit the various video contents which were prepared for this video course of NPTEL. Also, I want to thank all NPTEL staff and colleagues of IIT Bombay who helped me at various times to develop this course and to make it more meaningful for the society. So, with this I want to end my this video lecture of NPTEL on this course of Geotechnical Earthquake Engineering. I want to thank all of you who are listening to this video lecture and getting benefit from this lecture. You can see here my contact email address. So, if you have any doubt further on this course or on this topic, you are free to contact me by these email IDs. Thanks a lot for your patience hearing of this course.